Hello math students, today's video is lesson 3.1. In this lesson we are going to get a brief introduction to rational functions, which is what we are going to spend the rest of Module 4 learning about. The first part says Jacob is celebrating his 18th birthday. His girlfriend Holly knows the perfect gift for him, but it costs $360. She can't afford to pay for this on her own, so she thinks about asking some friends to join in and share the cost. So we want to know, how much is each person going to pay if we split it various ways. So if we have two people splitting the cost, we're going to take our $360, divide it by 2. If we had 3 people, we're going to divide by 3. That's going to be $120. If I divide it by 5, it's going to cost everybody $72. If we divide it by 10, it's going to cost $36. And if Holly can get 100 people to split the cost, it will cost everybody only $3.60. So we're going to take this information we just found to come up with an equation for a function that we can use to figure out how much it's going to cost for X number of people to split the cost. So on each part of the previous question, there's 2 things that were the same. Each part had a 360 and each of them had division, or I'm going to write it as a fraction. The thing that changed is the number of people. So this would be my function. And then if I want to sketch a graph, I'm going to just put some points on based on what the work we did on number 1. So if there's one person, so if Holly was the only one doing it, it's going to cost her $360. 2 people brings the cost down to $180. If we had 3 people, it brought it down to $120. 5 people brought the cost down to $72. 10 people was $36. And then 100 people was a whopping $3.60. So when I go and connect, the graph goes and does something like this, but a lot smoother. So this is just if I have with just the people. So I can only have positive, and technically I should only have integers or whole numbers. So 1, 2, 3, 4, 5, etc. If I was to take this whole scenario away and plug negative numbers in for x, my graph goes and does something like this. There's a couple things I want you to notice about this graph. First, on the x-axis, my graph gets really close, but it never quite reaches it on the left and right side. This is called a horizontal asymptote. On the y-axis, my graph gets really close on the top and bottom, but never quite reaches. We call that a vertical asymptote. So this kind of function is what is called a rational function. The definition of a rational function is it's any function such that f of x equals p of x over q of x, where P and Q are polynomials and Q of X is not equal to 0. So in other words, a rational function is a ratio between two polynomial functions or a fraction. So below are some examples of rational functions. Like other functions we have studied, rational functions come in different forms, with each form highlighting different aspects of the function. This first one right here is what we call the parent function. We'll come back to this a little bit later. But a parent function is simply the most basic form of a function. So there's a couple features about a rational function that we're going to talk about right now. We're going to talk about roots and vertical asymptotes. When we did polynomial functions in Module 3, we found the roots by setting the function equal to 0. If I want to find the roots of a rational function, we're going to do the same thing, except the only thing we care about being equal to 0 is the top of the fraction, because the bottom of the fraction can never be equal to 0. So to find the roots, you're going to set the numerator, which is the top, equal to 0. So for this particular function, I'm just going to set the top equal to 0, which means x is equal to 3 and x equals -1. Because I'm just setting each factor equal to 0. Vertical asymptotes we saw on the previous, or the question 2. It's just that line that my graph gets really close to. If we look at the equation, we should notice that if I put a 0 in for x right here, it gives me an error. We can't divide by 0. On the graph, at 0, that's where my vertical asymptote is. So vertical asymptotes happen when the bottom of a fraction is equal to 0. So to find the vertical asymptotes, set the bottom of the fraction, or the denominator, equal to 0. So for this example, I'm going to say x times x minus 1 times x minus 4. Set that equal to 0. Gives me x equals 0, x equals 1, and x equals 4. One thing I do want to point out is a root is a point on the x-axis. But an asymptote is a vertical line. So an asymptote, we don't actually have the line itself is on the graph, but my graph approaches that line, if it was actually there. So the last thing that we're going to do in 4.1 is we're just going to review function transformations. So if you recall, if I have a number that I am adding onto the function, that's going to move me up. If I have a number that I am subtracting directly from the x, that moves my graph to the right. So what we're going to do is I'm going to take these graphs and I am going to, for the first part, move them up 3. So every point goes up 3, like so. And then for m of x, I'm going to move everything right 2. So we're going to do the same thing for the next 3 functions. So this is what my graphs for the transformations of x squared are going to look like. I just took the parabolas, moved them up 2. For the square root, same kind of thing. I took the square root, moved it up 2. For m of x, took the square root, moved it right 2. With the rational functions, what I really am looking for is that my horizontal asymptote for t of x moved up 2 units. So the main shape of the graph is the same, it's just moved up 2. For m of x, I've moved my vertical asymptote right 2.